Hello and welcome to this lesson on enthalpy changes for year 1 of the OCR chemistry course. A lot of the ideas that we're going to talk about today are familiar to you from GCSE, but there are some new technical details and some new definitions that you'll need to learn. So let's make a start. Okay, so for your starter, just some quick recall questions from GCSE, so pause the video here, jot your answers down on a piece of paper and we'll come back in a moment. Here are the answers for those starter questions. You can review your work. We'll come back and talk about some of these things throughout the lesson. So what is enthalpy and what are enthalpy changes? Throughout GCSE, we've probably used the word energy to describe enthalpy. So enthalpy is just a measure of how much heat energy is in a system. And we can't measure that quantity directly, but we can measure the enthalpy change when a reaction happens. The enthalpy change is given this symbol, delta H, so that little triangle is the symbol delta, means change, H is enthalpy, and that quantity is measured in units of kilojoules per mole. All enthalpy changes are measured under standard conditions, and you must learn these. They are a temperature of 298 Kelvin, a pressure of 100 kilopascals, and where solutions are concerned, a concentration of 1 mole per decimeter cubed. You might see in some older textbooks a pressure of 101 kilopascals or 1 atmosphere quoted, but our specification requires 100 kilopascals. Enthalpy changes are also measured with reactants and products in their standard states, and that means what physical state, solid, liquid or gas, would that element be in under standard conditions. We can represent the enthalpy changes that are happening in a reaction using an enthalpy profile diagram. You sketch these for your starter. You can see on the left we've got an exothermic reaction and on the right an endothermic reaction. In the exothermic reaction on the left, the products have less enthalpy than the reactants and therefore the enthalpy change is negative. This will result in a temperature increase because that energy has been given out to the surroundings. For the endothermic reaction, the products have more enthalpy than the reactants and therefore the enthalpy change is positive. That's going to result in a temperature decrease because energy has been taken in from the surroundings. You're probably familiar with the term activation energy from GCSE. Breaking bonds apart requires an input of energy, and so to make any reaction happen, we have to put energy in to start with. The amount of energy that we need for that reaction to take place is called the activation energy. On a reaction profile, that's shown by this arrow you can see in green, and the arrow always goes from the enthalpy level of the reactants to the top of our curve. So at this point we're going to do a little bit of practice. There are 2 reactions here, the enthalpy changes have been shown for you, and I'd like you just to sketch enthalpy profile diagrams for those reactions. They don't need to be to scale, but they do need to be labelled fully. Pause the video here and have a go. Here's what your enthalpy profile diagram should have looked like. You can see I've put the reactants and products on the relevant lines, and I've also given the value for delta H next to the arrow. If I'd been given a value for activation energy in the question, I would have put this next to the green arrow as well. Often in exams you'll be asked to label the axes on these profile diagrams, so remember the x-axis is progress of reaction and the y-axis is enthalpy. Now we're going to go through 4 different definitions for enthalpy changes, and they're specific to different types of reaction. We'll talk about each one in turn a little bit more later on. The first is the enthalpy change of reaction. You can see here next to the delta symbol we've got a little r, that r is for reaction. The definition for this is that the enthalpy change accompanies a reaction of the molar quantities shown in a chemical reaction, under standard conditions and with all reactants and products in their standard states. The second definition is that of enthalpy change of formation, and you can see next to the delta there's an F for formation. This is the enthalpy change that takes place when 1 mole of a compound is formed from its elements under standard conditions with all reactants and products in their standard states. You'll see this section in purple is identical for both of these definitions. The third definition is the enthalpy change of combustion. Again, next to the delta symbol we've got a C for combustion. This is the enthalpy change that takes place when 1 mole of a substance reacts completely with oxygen, under standard conditions and with all reactants and products in their standard states. The final definition is that of enthalpy change of neutralization. Next to the delta symbol, we have the letters N, E, U, T to represent neutralization. This is the enthalpy change that accompanies the neutralization of an acid by a base to form 1 mole of water under standard conditions with all reactants and products in their standard states. So you can see from these 4 definitions, the part in purple is identical. You only need to learn that once. The other parts you will need to memorize. And it's really important that you know which thing there is 1 mole of. You'll see why later on. So a little bit more about enthalpy change of formation. You can see here, our definition says it takes place when 1 mole of a compound is formed from its elements. So let's look at an example. We're going to look at magnesium oxide formation. If I write the balanced equation for the formation of magnesium oxide, it's this. So 2Mg plus O2 makes 2MgO. And my enthalpy change for that reaction is minus 1,204 kilojoules per mole. However, that doesn't fit the definition that we have in the box at the top of forming 1 mole of product. I'm forming 2 moles of product in this equation. So in actual fact, the enthalpy change of formation for magnesium is represented by half the enthalpy change of the reaction, i.e. minus 602 kilojoules per mole. By very definition, the enthalpy of formation for any element is going to be 0. It already is itself. So, what I'd like to do is to pause the video here and have a go at these questions to summarise what we've learnt so far. Here are the answers for those questions. You might want to pause the video here again to check through your work. Next up, an exam question. Pause the video, have a go, and we'll come back and look at the answers in a moment. Okay, so hopefully you got these answers. If you didn't, we're just going to talk through how we got there. Part 1 asks us to calculate the enthalpy change when 240 decimeters cubed of N2O, measured at room temperature and pressure, is formed from nitrogen and oxygen. In the enthalpy profile, we can see that the reaction is endothermic. It takes in energy from the surroundings, and it takes in 164 kilojoules per mole. But that is when 2 moles of N2O are formed. So to form 1 mole of N2O would take in 82 kilojoules per mole. In our question, they've asked us about 240 decimeters cubed. Now, from our studies earlier in the year, we know that 1 mole of gas, measured at room temperature and pressure, will occupy the molar gas volume, or 24 decimeters cubed. So that means that we've got 10 moles of N2O. Remember, from the enthalpy profile, we know that formation of 1 mole will require 82 kilojoules per mole, so the formation of 10 moles will require 10 times that, or 820 kilojoules per mole. Part 2, what is the enthalpy change of formation, delta HF of N2O? Again, we work that out from the diagram, it's 82. And finally, part 3, calculate the activation energy for the reverse reaction. This relies on the knowledge that the same amount of energy will be taken out in one direction as is taken in the other direction in a reversible reaction. We know that this reaction takes in 164 kilojoules per mole, so the reverse reaction will give out 164 kilojoules per mole. The activation energy is going to be the difference between the activation energy on this enthalpy profile in figure 5.3 and the energy taken in this reaction. So it would be 447 minus 164, which gives us 283.